Hello everyone. Today I'm going to present deterministic phase transition and self-organization in logistic cellular automata. I would like to start by thanking APS organizers for this opportunity despite the fact that the actual meeting was cancelled. So this work was done together with Muhamet Ibrahimi and Oğuz Gülseren. My name is Seymur Jahangirov. I'm an assistant professor at National Nanotechnology Research Center, which is inside Bilkent University in Turkey. Professor Oğuz Gülseren supervised Muhamet Ibrahimi's thesis, which is basically this work that I'm going to present. And I would like to thank also Muhamet Ibrahimi for sharing his master thesis slides with me, which are basically the foundation of this presentation. And I would like to thank Turkish Academy of Sciences, TÜBA, for supporting this study. This study was published in PRE, and you can refer to that article for further information. So here's a sort of outline. I will start with concepts that is very familiar to many people probably, with cellular automata, logistic game of life. I will describe cellular automata, CONWAY'S game of life, logistic map. Then we will present how we bring them together in the logistic game of life. Then we will talk about self-organization and the application of the similar principle in a different automaton, namely Rule 90. And then I will conclude with some discussions. So cellular automata models were used to investigate self-replication. Some physical models like diffusion limited aggregation can be considered as cellular automata. It's used to understand fluid dynamics like in the lattice gas automata or lattice Boltzmann method. And it's used to understand in general the nature itself, how patterns emerge in nature. And much recently it was used to explain the patterns that emerge on the skin of an actual animal, a living cellular automaton. Okay, good. So cellular automata goes back to von Neumann, and basically if we have to summarize cellular automata, we can talk about discrete cellular space. It could be hexagons or cubes or square grids. The states are discrete, namely it's 0, 1, or maybe in the von Neumann's replicator case it's 0, 1 to 3 up to 28, and it moves in discrete time, and there is some neighborhood range which we name as M, and some rule set. Okay, so for example, this is an example of a Moore's neighborhood range which has 8 cells. So basically the fate of this cell may depend on what these cells are. And this is a simple one-dimensional cellular automata where the neighborhood is just 2 cells. Okay. So Conway's game of life dates back to 1970s. I'm sure many people have heard of this. So basically here we want to point out that the dynamics of the system, the rules of the system is very simple, but the dynamics is complex. And we basically summarize the rules here with these 3 lines. So if the Moore neighborhood in total is 0, 1, 4, 5, 6, 7, or 8, then the system decays. No matter whether it was 0 or 1, this cell will go to 0, which we consider as decay. If it's 2, then we have stability. 0 goes 0, 1 goes to 1, and if it's 3, it's growth, because both 0 and 1 would be mapped to 1 as seen here. Okay, Conway's game of life have been studied a lot, especially the statistical mechanics side of it. Excuse me for this video not working properly. I'm doing this presentation on a rather old computer, but normally, but still you can see the richness in this system. And here is some literature that I'm not going through each one of them. Just let me point. For example, Perbach has a Nature paper where he shows that Conway's game of life is a self-organized critical system. Okay, there are other studies that are also very important. So please ignore these gliders that should really glide. Okay, the system has stopped. It means that I've talked too much about this system. Okay, good. Let's move on to the logistic map. I'm sure you are also very familiar with the logistic map. Here again you have this parameter that controls a 1D mapping. So you start from a certain point, it goes back and forth, and sometimes you enter in a loop that has a period 1, sometimes period 2, sometimes period 4. And if you plot these periodic structures with respect to the parameter, you will get this bifurcation diagram, which is a typical bifurcation route towards chaos. So we basically combine the idea of game of life and the logistic map here. First of all, we rewrite the rules in a finite difference form. You remember this was the initial version. We don't change anything, we just rewrite it as a SRT plus 1 is equal to SRT plus delta S. In this case, delta S is basically minus S in this case. You can see to go to 0, you have to subtract S from here, which means delta S is minus S. If it's stability, delta S is 0. If it's growth, delta S is 1 minus S. And you can see here the neighborhood is 0, 1, 2. So basically red, again, let me remind, corresponds to decay, blue is stability, and green is growth. So what we do is, in the spirit of logistic map, we add lambda in front of these changes. And lambda is any number between 0 and 1, any rational number. By the way, it can be also bigger than 1, which I will talk in a moment. Not in a moment, later on, sorry. So basically, once you include this lambda, the states are no longer discrete. They don't need to be 0 and 1. They also can be any rational number, and their sum can be any rational number. The neighborhood sum can be any rational number between 0 and 8. So basically what we do is, since you can have any number, instead of having these discrete states that would lead to operations like growth, decay, and stability operations, we have now operational regions. Okay, and we fairly attribute these regions, like this one should have 1 space, this one also should have 1. Similarly, so T1, which is the border between this decay operation and stability operation, is chosen to be 1.5, and this is 2.5, and this is 3.5, T3. So basically you can see that including lambda, a single parameter, we are forced to include these other parameters, but we can still see a lot of richness by just changing lambda without changing any of these parameters. Okay, let's see what happens when we include this lambda parameter. When lambda is 1, you basically recover game of life. the original Conway's game of life. But as lambda goes down, you can see that the behavior doesn't change immediately, but the states become blur. And basically, while this system is running, okay, and you can see that as lambda is going down, you have this flickering states, and then so basically right now you have three different regions fighting for majority. There are stripes, there are flickers, and then there are zeros in between. And then you see a domain formation of these stripes, etc. Very rich system. Again, the video is normally much better, but in this computer you are seeing it in discrete time, sort of. Okay, so with this lambda, what this lambda is doing is, so basically when lambda is 1, when there is a decay, you go straight from 1 to 0. However, when lambda is something like 0.5, you have an asymptotic decay. And similarly, when you have growth, you go straight from 0 to 1 when lambda is 1. When lambda is lower than 1, then you have asymptotic growth. So our growth and decay become asymptotic growth and asymptotic decay. And we basically going to use these abbreviations. Decay is D stands for decay, S stands for stability, G stands for growth. Okay, now what happens if we start with any rational number in between 0 and 1? While you are operating on them with growth and decay, this continuous set will be approximated into a contour set like this, a lambda dependent contour set you can see here. And notice that every step of the contour set, the higher the order gets, the higher the polynomial gets here. So first order has polynomials in lambda to the power of 1, second order has lambda to the power of 2, etc. You may ask what happens to stability. Let me show that the regions here fade out eventually. Let me show you with numerical simulations. So let's start with uniform distribution. In the first step, you can see that this region almost faded out, creating these two regions. And if you keep on with step 2, step 3, and step 1000, you get the contour set. And here's another way of showing it. So basically, this is lambda, this is step 1, and basically log of occurrence. So basically, these plots are taken from these cuts over here. You can see that here you have large values, and then you have these things over here, etc. I hope it is clear. By the way, anything that is not clear, please write down in the comments below. I'm happy to answer them, or just email me. Also, the codes are available upon request. Now, what happens when you change lambda? So what happens is that this is Conway's game of life, and it remains like that until you hit 0875. Okay, and there is a phase transition here, but it's not just a simple phase transition. There are multiple phase transitions that continue. There is also, none of these are numerical errors. All of them has good reasons to exist, and we explained why they are there, at least why at these particular points they occur. So, and the nice thing is that our mean field approach reproduces these values over here, the density when lambda is in this range. And the reason why it works so well is because in this range of lambda, the system is really mixed and it's interacting, so the mean field approach works well, but however it fails over here. Okay, now what happens here is really important. Although game of life, Conway's game of life is really interesting system, it stops eventually. For example, if you take 1,000 by 1,000 initial like cells and start from initial condition, after 10 to the 5 steps, the system reaches equilibrium or inactive asymptotic phase, meaning that there is no activity left. So here we have a way of excluding these flickers which keep, so periodic orbits. So even though you have periodic orbits, we count them as zero activity. However, once you pass this critical threshold, you have a dense active asymptotic state. So you have an asymptotic state that is more dense than compared to Conway's game of life. Okay, why there? Why this happens at exactly this point? Now the reason is that so to understand this, we should think about this case, which happens quite frequently. Why it happens quite frequently? Because in the Conway's game of life, also in this region, zeros are everywhere. It's a prevailing structure throughout the system. And if you have only one growth operation, you go from 0 to lambda instead of going from 0 to 1. Remember in Conway's game of life. So basically, if you have such a system for lambda around it, let's look at here. This is lambda versus this 4 lambda. Okay, so when 4 lambda equals to T3, you can see that the operation regime goes from growth to decay, or it goes from decay to growth, depending whether you are increasing lambda or decreasing lambda. In this case, if we are coming from Conway's game of life, then we are coming from 1 and we are decreasing lambda, and we are basically passing from the decay operation to growth operation, which means that normally this system would, this S would decay, but now it starts growing. That's why there is a tendency to not stop instead of stopping. And you can see that we are able to figure out where these transitions are going to happen. They are going to happen at the places where the sums of these correspond to either one of these T1s, T2s, or T3s. Whenever 4 lambda is T3, there is a sharp peak here. Lots of 4 lambdas are T3. Again, this may be too much, and maybe I'm talking too fast. I'm happy to explain it further if you want. Okay, the other significant transition, let me go back a little bit. You might remember there is another significant transition here. In fact, this is the largest transition in the system, which also happens when the sum equals to one of these T1, T2, T3s. In this case, 3 lambda is equal to T2, which corresponds to lambda equals to 5/6. Okay, now as the magnitude of change in the density decreases, the magnitude of change in the density decreases as the sums M involve more and or higher order terms in the Cantor set. Okay, so you might remember in the Cantor set there were orders like lambda to the power of 1, lambda to the power of 2, lambda to the power of 3, etc. And as you increase the order, their occurrence is less frequent. Okay, here's a reminder. And since they are less frequent, the changes occur less and less. So basically here, this peak involves only lambda to the power of 1, and it's a sharp peak, and correspondingly it's a large change in the density. However, this second order thing which occurs over here has smaller peak, and it involves this kind of configuration where you have 3 lambdas but also this other part which is GG0. Okay, and then there are even higher order terms which will result even smaller transitions. All in all, if we look at these two main transitions, actually this transition over here at point lambda a and this transition over here lambda b, and if we plot these ones in log scale, you will see that you get a linear distribution, but also you still have these self-similar features, which is a signature behavior in this particular system that needs to be understood even better. And these red lines basically correspond to higher and higher orders being involved. Good. Now comes the mean field approach. I will actually skip it a bit quickly. Basically here we make a one-shot mean field approach, meaning that we take just the uniform distribution, then we calculate the neighborhood probability, the sum probability by taking this uniform distribution and taking the convolution with itself 8 times. In any case, after some mathematics, we can see that our mean field actually does not depend on lambda. That's why it was a horizontal line in the rho versus lambda plot. But some may wonder where it can be taken, whether it can be taken further by taking a 2-shot mean field, 3-shot, or maybe even infinite shot mean field approach, and see where it takes us. Okay, so this is basically, again, pattern formation here. Now we define here the pattern formation with a very nice correlation function, which is basically summing up the differences between the neighbors. So if you have zeros, then you get 0 in the correlation, and you can see that at the beginning zeros prevail, then they decay out. And then there are flickering regime, which is sort of between 3 and 4, and you can see that the differences, if you sum them up, it's around 3 or 4. Then there are stripes which correspond to correlation function being 6, and when it's 8, it's basically unstable for the whole range of lambda, while these stripes prevail as you go down in lambda. So basically the main part of this talk is sort of over. Now we go further with self-organization. So glider is an emergent propagator transmitting activity in the long range and also the key component of computational properties of Conway's game of life. And you can see what happens to glider when you change lambda. Let's watch it again. It preserves its shape, direction, and velocity in a continuous range of lambda, but at some point it dies out. So we wanted to understand what is this range that keeps the glider alive. Let us remind you these operators: decay, stability, and growth. So let's start with 0 fields, and this is 1 1 1 1 1, the glider, and this is step 0. So for example, what will happen to this cell? Actually nothing will happen to it. So let me find, so this cell should grow, so you get g times 1, which is also 1, by the way, because the growth applied to 1 gives you 1. Let's see what happens next. For example, this has grown. Let's go further. For example, this cell should grow, so the next time this should be G0. There you go. Okay, so while we repeat this, we get this features, the decaying cells that are left behind, but there is this feature that emerges here that keeps repeating. Okay, behind any stable, oscillating, or propagating structure, there is a pertaining finite set of local interactions involved, and this is seen here even better. And we quantify these interactions by investigating the corresponding neighborhood sums under the operations, meaning that, excuse me, for example, here this cell has these summations, so G0, DG, GG0, GG0 summation, which means that this cell will preserve its operation regime only if the polynomial, this fourth order polynomial here that corresponds to the sum around it, preserves its position in the operation regime. In particular, there is one that is breaking this, and that's why the glider is dying around 0.75. And the reason is this 11th order polynomial, which is also plotted here. And the moment that polynomial passes between decay and stability, basically the cycle is broken. So due to the self-generating character of these interactions, you can see that this is the first stage and this is the last stage, and you can compare this and this, you will see that they are equal, meaning that there are these interactions that keep repeating, so keep catalyzing themselves. That's why we call them autocatalytic interaction sets. Okay. As lambda is tuned, we notice the step-by-step emanation of another propagator which does not exist in Conway's game of life. Let us show how. So at the beginning, let's start with this. You can see that it's a growing structure. Now we will start again with the same initial conditions, but with lambda equals 0.9. And you can see that it just had a few steps, then it also broke down. Then this will have further steps. It was almost going to propagate, but then it also blew up. Then you can see that this goes even further, and when you are here, you are in this magical regime where this system actually propagates, and it's a period 36 propagator that is living in this very careful place. Okay, this should be, yes, there it is. Now we named it RAYFISH because of the way it swims and the way it looks like a rayfish. And you can see that outside this regime over here, it also blows up. So this animal, period 36 propagator, actually lives in this autocatalytic regime, which is shown by this lambda A. So you have to be bigger than lambda A and smaller than lambda R. Lambda A is actually familiar to us from before. Is when 3 lambda is equal to T2, and basically it supports this stage, this very important stage, because in this case you can see after 3 lambda there is a growth here which helps to enter to this scheme, and it's an important part of the propagation. You can see there you have 3 lambdas, which makes this nose. If you are below lambda a, nothing like that will happen. And then there is the upper limit lambda r, which is found just like in the RAYFISH case by calculating this yet another kind of 11th order. It happens to be also 11th order polynomial, and the solution is lambda r. Okay, a spatio-temporal synchronization of values and operations effectively exploit the different symmetries of the framework, thereby introducing consonance in higher hierarchy, even though only local interactions are involved. So you can see how robust this structure and how inevitable this structure, and one of the ways that it's inevitable is that some of these parts are really simple, while on the other hand it's very interesting that some of the middle parts are really complicated. So since you have these simple parts, you enter this loop and eventually you go and you make these complex structures as well. Inevitable, that's the key word here. Further emergent behavior, as I promised, when you have lambda bigger than 1, you will get different behavior. Again, sorry that the video is not working properly, but I can give you the codes, and in the codes they look really nice. You can see that as lambda changes, there are several new propagators emerging. There are several new ones yet to come. There they are, and this is very interesting system on its own. Okay. Now we would like to apply this idea of logistic cellular automata to other kinds of automata. One simple way to extend it is to think about Rule 90, introduced by Stephen Wolfram. Basically, here we have one cellular automata. Again, the system is AUTOCATALYTIC, meaning that the fate of this cell depends only on the summation of these values, right? And we only have decay and growth here. We don't have stability. And basically, if you run this with a single cell, you will get this Sierpinski triangle. While if you run with random initial condition, you will get this thing that looks chaotic. Another thing that is important are the classification introduced by Wolfram, meaning that class 1 is basically same uniform final stage, class 2 periodic stable structures, class 3 aperiodic behavior, and basically class 4 is localized complex structures, something between this one and this one. Class 4 is between class 2 and class 3, sort of. So we apply our typical procedure here. We write things in terms of delta S, and then we put lambda in front of it. And what we get is, at the start, it behaves just like Rule 90 would behave, but as lambda changes, you have several phase transitions. And in fact, here, one nice thing is we reach at period 3 stripes, which will be really important. So what you see here with black lines are basically contour set polynomials, while this blue line is period 2, if you had like A going to B, B going back to A, and this magenta line which is creating these ones are like these stripes. And to create these stripes, you have to have growth, and then decay. That's why these magenta lines should all be in the relevant region. And you can see that they come into the relevant region only here, and that's when these stripes begin appearing. So here they are, growth, decay, coming back to itself, and we are making a sort of transformation here where the stripes are set to zeros so that you can see the behavior on top of the stripes even easily. Here the crucial thing is that we believe that as the lambda parameter is changing, we are smoothly moving from class 3 behavior, chaotic behavior, into class 4 behavior. And you can clearly see that here it's quite chaotic. Then these propagators emerge, and how they emerge, basically as we change lambda, this period 3 becomes more and more favorable, so they squeeze out these chaotic regions into propagators just like this, which interact with each other in a complex fashion. Another very interesting thing happens here at this critical moment. This propagator, which I believe is period 18 propagator, turns into period 48 propagator, because the autocatalytic interaction set of this one is no longer supported, while this one now becomes supported. So we basically feel like this is very similar to the punctuated equilibrium, whereby organisms suddenly change their phenotype according to the outer world. Okay, so this is the last slides. Basically, these are the last slides. Our methods can be applied to other kinds of automatons. You can see how they can change with respect to lambda, and in fact this is very interesting, worthwhile waiting for the video to run. You can see that even with different rules, it's not game of life, it's different rule named 34 life, you get similar behavior, similar kind of stripe formation, but there is further interesting behavior here. Let me run faster. You can see sort of wave-like structures that are produced, which are reminiscent of Belousov-Zhabotinsky kind of wave-like structures, or the CAMP waves in these different animals, etc. Okay, without further ado, let me finish here, because we already spent too much time on these structures. This is another application of the logistic version. So here you can see one of the larger than life procedures, and here you can see the logistic version. In summary, we introduce a method that brings richness to the usual kind of cellular automata. We believe that this system is quite rich and very interesting for people from different fields. I would like to thank you for your attention. The details are here in the paper. Please ask any kinds of questions. Thank you all. Have a nice day.